Okay, fixed my battery problems, and now we're off and running, and we're going to finish up our discussion here. We've been talking about amines and how to name them. We've got a couple of different ways to name them depending upon the situation. Let's just look at another example. Here I have an amino group on a cyclohexane. In this particular case, because it's on a cyclohexane, the easiest way to name it by far is just to refer to it as an amino cyclohexane. I suppose I could call it a cyclohexanamine, cyclohexane minus the E plus amine, cyclohexanamine. That would work as well. But I think aminocyclohexane is probably a little bit more clear. What if we had the same amino group, but now we put a couple of other substituents, maybe a couple of ethyl groups on that nitrogen? This then becomes N, N diethyl. N, N refers to the location of the ethyl groups, both on nitrogen. N, N diethyl cyclohexanamine. In this case, with those extra substituents on there, it's going to be more difficult to name this aminocyclohexane. I suppose you still could. NN diethyl aminocyclohexane would work. I think that name works best here when there's no substituents on nitrogen and doesn't work quite as well here, but the truth is IUPAC allows for both of them. So if one of them feels better to you or flows better off of your tongue, then by all means use it. You do have options when you're naming amines. I mentioned ammonium ions. Let's just see how those ammonium ions can form. A real common way for an ammonium ion to form is to take an amine, which is an organic base. It's a weak base, not a strong base, but it's an organic base nonetheless, which means simply that if you introduce an acid, let's say HCl, the amine will be basic and it will pick up an acidic proton. The amino nitrogen has a lone pair which can pick up the acidic proton and give you a protonated ammonium ion. And this would now be an ammonium chloride, more specifically a butyl, because there's a butyl group there, ammonium chloride. Let's look at this aeroformalism. The basic electrons are the lone pair electrons, and they pick up a proton, an H+. But we never see the H+ as such. Instead, H+ is delivered from HCl in the following way. We pick up the hydrogen without any electrons. The 2 electrons of the hydrogen-chlorine bond go to the chlorine. This is delivered as H+, producing the ammonium ion plus Cl-. So a butyl ammonium chloride is formed there. So ammonium ions are important. We'll see them from time to time, and this is a very typical way in which to form one. We're almost done. We've got a couple more functional groups to look at. Let's see what we've done so far. We've looked at alkyl halides, done. We've looked at alcohols, done. We've looked at amines. All that's left are to look at ethers and sulfur-containing compounds. It's going to be quick discussions in both cases. Ethers. In the case of an ether, you have an organic group which is attached to an oxygen, and then the oxygen is attached to another organic group. Looks a lot like water, except that we've replaced the 2 hydrogens of water with these R groups. So this is water, and this is an ether. These R groups can be anything you like. Now I mentioned when we're making organometallics that we do require an ether solvent. A very common solvent to be used as an ether is this one, diethyl ether. Very, very common ether solvent. But ethers come in a lot of different varieties. You can even put the oxygen inside of a ring, and this is an ether. This particular ether, which has an oxygen inside of a ring, is a sort of a famous one called furan. And if you completely hydrogenate it, which means get rid of those pi bonds and replace them with just carbon-hydrogen bonds, then now you've got an extra 1, 2, 3, 4 hydrogens compared to furan, and we call this tetrahydrofuran, or THF for short. That's a very common organic solvent. Diethyl ether is a common solvent, and so is THF. Those are both ether solvents. Ethers are important compounds for a lot of reasons, not the least of which is that they are very popular solvents. And so I already showed you these organometallic reactions. Let's review. If I needed to produce a Grignard reagent, I might use diethyl ether as my choice of ether. This metal, magnesium metal, is required to make the corresponding Grignard reagent, and the ether is simply the solvent. Now, why is this reaction so fussy? Why does it require ether? It turns out that this metal in this particular reaction is literally just a chunk of metal. So you take a little chunk of metal, and there's a blow-up picture of a little metal particle, and the alkyl halide bumps into the metal, and that initiates a reaction which ultimately leads to the formation of this Grignard reagent. Now, this Grignard reagent is not very soluble in much of anything, and if we didn't have ether around, it would just lay on that magnesium chip. What would essentially happen is that the magnesium chip would be coated in Grignard reagent, and as soon as it was completely coated, that would stop the reaction from continuing, from progressing, because the magnesium that was left over on the interior of the chip or the particle would not be accessible any longer. It would be completely coated. The ether is one of the few solvents which can solvate a Grignard reagent and lift it off of the chip, allowing more magnesium underneath to continue to react so that you can have a reaction with decent yield. That's what the ether does. Without that ether in there, it's a very low yielding reaction because you very quickly coat the magnesium chip and the reaction stops. So that's the role of ether. How do we name these things? Well, I already showed you a couple of names, but let me just give you one or two more. This is an unfair description or an unfair picture because we haven't talked about aromatics yet. So let me redraw it in a way which probably looks a little more reasonable. You can just ignore this picture for now. We'll talk more about that representation of a benzene ring a little bit later. Here it is drawn in a different way. This benzene ring, when it's a substituent, is referred to as a phenyl group, and here is clearly a methyl group. So in this case, we have a methyl and a phenyl ether. We're just going to place them in the name according to alphabet, M before P, so this becomes a methyl space phenyl space ether, a methyl phenyl ether. If you had a propyl and an ethyl, E comes before P, so this would just simply be ethyl space propyl space ether, and you'll get the hang of it. Last topic, sulfur-containing compounds. If you look on a periodic table, you will see oxygen in the second row of the periodic table, and right below it in the same column is sulfur. Sulfur behaves a lot like oxygen. They're essentially the same atom. Sulfur is a big version of oxygen. It's not really true that they're the same atom, but they have a lot of similarities. Bottom line is, whenever you have an oxygen compound like an alcohol, you can have a corresponding sulfur compound. This is, whoops, gotta spell. This is an alcohol, and this is a thiol. The sulfur version of an alcohol is just called a thiol. And likewise, if you have an ether, we're just going to refer to this as a thioether. So thiols look a lot like alcohols, and thioethers, there's another word actually called sulfide, which means the same thing as thioether. Thioether or sulfide are the sulfur versions of the oxygen-containing ether compounds. And that's really all you need to know about sulfur compounds for now. So that concludes our chapter. You are now ready to tackle all of the homework problems from Chapter 6, as well as Chapter 5 and Chapter 4, and you need to do that all before Friday in order to prepare for the exam. I'll see you Friday.